Hi class, so today we are continuing on with hypothesis testing and we're going to learn about that fifth step. So previously in chapter 9, we focused on those 4 steps just generally. So go ahead and I'd like you to review your notes on what you had taken as those key points. And then the statistic we're going to be using in step 3, which is computing the test statistic, and the data is given, is our z-score from chapter 8. So these are our critical values. So if you remember, step 1 is setting up your hypotheses. Remember, you have 2 hypotheses, the null and the alternative. You also need to know what kind of prediction am I making? Am I making a directional research hypothesis, one direction, one tail? Am I making a non-directional research hypothesis with 2 tails? You're also going to see that it's stable and static for our Z critical scores or critical values or boundary scores. There's a number of different ways we can call them. So once you've identified if you're using a 1-tail or 2-tail test and you've set up your hypotheses appropriately, then step 2 is finding those critical values. Those critical values are set, so refer to this slide when you've got different questions. And then step 3 is going to be collecting our data. So with our data, we have our z-score from chapter 8. So I just wanted to kind of go over it again. We're going to see as we get through inferential statistics, the first ones we're going to be learning are going to be looking at mean differences on the top, and then what's going on with variance at the bottom. And so our numerator is just looking at that, the mean difference, taking that sample mean and then comparing it to the known population mean. And so that we're looking for to be big. Ideally, we want big on top and small on bottom to maximize, to get a larger z-score so we can reject our null. At the bottom of the z, it is standard error. So standard error is interpreted just like standard deviation. And then there's a couple things we're going to have to do. So remember, your standard error formula is population standard deviation over the square root of n, or the square root of variance over n. And most commonly, I will give you standard deviation. So again, ideally, we want big on top, little on bottom. When we're doing a formal hypothesis testing, it would be your looking at, again, your sample mean minus your population mean, and then going over standard error. So kind of breaking down the formula we learned in chapter 8 a little bit more. And so then, again, my goal for us, and any test statistic we have, we're mostly going to want big on the top, little on the bottom. Again, so we can get a bigger number in hopes that we get in that critical region. And so then we calculate that z. You're already familiar with calculating that z, and then you make a decision. So again, your decision, if you're in the critical region, the shaded area, it's reject the null. If you're in the white space, it's fail to reject the null. Reject the null. I found evidence. Fail to reject the null. I don't have enough evidence. So this is a drawing showing a 2-tail test, a non-directional research hypothesis. It would look different and just have one of those tails if we were doing a directional research hypothesis. I do have these 2 little quick checks. You can kind of pause or even have the slides open and see which answer you have. And I have the answers posted in the slides. And so this is my second question I'd ask you. Again, making those comparisons between here's our critical value. How do we make that decision? If I have this z-score, again, if it's in that shaded region, bam, we can reject the null. All right, so that was the 4 steps, and now we're adding step 5, which is effect size testing. So the first 4 steps are part of the null hypothesis significance testing. It is telling us if things are significant or not. Step 5 is kind of giving us a real-world picture of what's going on with our data, and so we're going to learn about 2 different effect size calculations, Cohen's d and eta squared. Eta squared is actually a Greek symbol, and we're not focused on that for our z. We're focused on Cohen's d. So Cohen's d is the most common effect size measure. It is going to be something we see with each test statistic. It's just the formula is going to vary a little bit differently. You're going to see for this one, it's the same top that you had in your z formula, but the bottom is the population standard deviation. And so this is kind of like independent, regardless of sample size, what would the main effect be? So you calculate Cohen's d. So you take same numerator you did for z, and then divide it by the population standard deviation. The number you get can then be classified with what's above. So this guy right here is going to help us determine if we have what size of effect we have. If you have a z-score less than 0.2, it's no effect. All right. So 0 to 0.2 is no effect. It is done where you would have a positive number. If you have a negative sign, ignore the sign. So 0.2 to 0.49 is small, 0.5 to 0.79 is medium, and 0.8 is large. And that effect size really gives us a genuine idea. It is also interesting to note that if you calculate effect size when you fail to reject the null, and then you do have something 0.2 or greater, that's an indication you probably had a type 2 error. If you go through and calculate effect size and you said I reject the null, and then you get something less than 0.2, that is an indicator you probably had a type 1 error. So a lot of newer research is always calculating effect size, though you may come across instructors as you move forward in research or research methods that say just calculate effect size if it's significant. But our new wave of statistics is we calculate it anyways to give us a good gauge. So that connects kind of to this idea of practical significance. Okay, so I am now going to go ahead and pause, and we're going to now put everything in action with a problem and giving you an example problem. So go ahead and get out a scratch piece of paper, have some notes handy, and we're going to be working through these 5 steps. All right, it's time for our example walkthrough. So I'm interested in nutritional benefits of blueberries, and I'm interested in working with an older population. So I'm going to go ahead and work with individuals that are greater than 65, and I'm wanting to see is adding blueberries to their diet, does that impact cognitive scores? All right. So I've got, from a population of older adults greater than 65, I've randomly sampled and selected 25 individuals. I am asking them to increase their daily dose of blueberries for 6 months. And I probably would prescribe a particular amount of blueberries. It could be, let's say, a cup a day for 6 months. I then am going to have, I'm interested in looking at how does that impact cognition. So there's a couple of standardized tests out there for cognition, and one of them is the Wisconsin card sorting task. And so I'm going to have them do that. So after they've been on this diet of blueberries, I give them the cognitive card sorting task. For the cognitive card sorting task, the population average score for adults older than 65 is 80, with a standard deviation of 20. I then look at the mean for my sample, and I have a mean of 92 on that Wisconsin card sorting task. All right, so we are going to need to do a hypothesis. We are going to need to find our critical regions. I am going to have it as a two-tail because that is the most conservative approach. We typically only use a one-tail or one-directional when we've got a priori research solidifying this really is the case. And best practices would be, I'd also pre-register it. So a lot of our examples are going to be two-tail. So I'd like you to go ahead and develop a hypothesis. So you're going to develop your null, you're going to develop your research, then you're going to go back to that table I had and look up what is the 2 z-scores needed for an alpha of 0.05. So go ahead and pause and take a moment to do that. We know we're using our z, and so I do have this information noted. This is all the stuff you need to use our z-score formula. We do need standard error at the bottom, so that's going to be something you're going to do first, and then we'll make a decision, and then we will do effect size. All right, so when setting up your hypotheses, you need words and math. So the math part, you have 2 different options. You can leave it very generally, and I'm saying that my group of individuals who have blueberries are going to be different than the general population. All right, so that's my alternative or research, and then they're the same as the null. I can also put this in specifying that population value, but knowing my hypothesis is all derived around the addition of blueberries, the treatment of blueberries. And so I can say mu is equal to 80, mu is not equal to 80. And again, that value of 80 is that population mean, right? So I'm saying my treatment in blueberries is going to be similar to the everyday older than 65 IQ cognitive sorting task score, or it's not, right? So that value that's placed there is the mu value. It is not your mean value. Your mean value is part of the test statistic, which you're making the comparison. You also need to do this in words. So here's a general example, very generic. Ideally, I'd like you to put in our independent variable of sampling blueberries and our dependent variable, the Wisconsin card sorting task. There will be a difference in cognitive scores eating blueberries for older adults older than 65, and there will not be a difference in cognition or cognitive scores when eating blueberries for adults older than 65. All right, so ideally, I'd love for you to put the context in there. Step 2, your critical region. If you were to pause and go back to that slide, you would see our critical value is plus or minus 1.96. Right? So if I calculate my z-score and I get a z-score of outside of 1.96, either positive or negative, I will have a significant finding. Ideally, you want to improve cognitive scores. So ideally, you're looking for that positive value. So then I'm going to go through and do my calculations. So the first step you're going to need to do is calculating your standard error. So I'm taking my population, standard deviation of 20, and my sample size of 25. Then you need to create your Z. So taking your sample mean minus your population mean over your standard error. So go ahead and take a moment to see and calculate what you get with that. So if you had gone through your calculations as I did, you would have gotten a score of 3. 3 is in that critical region for our distribution. It is outside or greater than 1.96. If it's in that critical region, what decision do I make? Remember, your two options are reject the null or fail to reject the null. So go ahead and take a moment to figure out what that is, and then figure out what does that mean in terms of blueberries and cognition. So in my step 4, I would want to state the decision. So I'm rejecting the null because I'm in that critical region. I also then want to make a statement. What does that mean? How do I interpret that in terms of my study? So I could say something like taking blueberries had a significant impact on cognitive ability of our sample. I can even say a significant improvement, and I can say improvement because I know there was an improvement because I got a positive Z. My sample score of 92 was above that 80 in the Wisconsin card sorting task, right? So step 4, I'm going to need you to always include 3 elements. So I'm going to share what those 3 elements are right now. So please take a note of this, and this is something I'm going to expect you to report in your homework and beyond. The first thing is you got to tell me the decision, reject the null or fail to reject the null. All right, so please do that. That's going to be an obvious marker. The other thing that I want you to include is terminology of is it statistically significant or not. Anytime you reject the null, it is statistically significant. Anytime you FTR it, fail to reject the null, it is not statistically significant. So please include that wording as well to make that connection. And then the last thing I would like you to do is, again, relate that interpretation back to your hypotheses. What findings did we have that we're generalizing to the population? So again, I could say taking blueberries improved cognitive ability. All right. So that is our 4th step. So let's go ahead and take a minute to talk about step 5. Step 5 is effect size. So the one we've learned so far is Cohen's D. So remember from Cohen's D, it's going to look similar to the top of what you did for your Z-score formula, but the bottom is just the population standard deviation. Once you get that D and calculate it, you then are going to put that number onto our table and determine if is it a small effect, a medium effect, or a large effect. Again, even if we have something that's a not significant finding, I still would like us to do effect size testing in the new statistics as a guide of possibilities of type 1 error or type 2 error. Let's take a moment to do that. So go ahead and pause the video, look back and see you had a sample mean of 92, you had a population mean of 80. That's going to be your top, and you get a standard deviation for the population of 20. So you're going to plug those in. So plugging those in, I'm getting 12 divided by 20, which equals 0.6. If I go back to those guidelines of where 0.6 is, 0.6 is in the medium range. So this is what something I might say. I definitely want you to include your D, your Cohen's D calculation. I then want you to interpret it. You could say small, medium, or large. So in this example, rather than saying medium, another adjective I could use is moderate. So a daily dose of blueberries over 6 months had a moderate effect on cognition. All right, so again, I got that from looking at my Cohen's D. All right, let's go ahead and look at, well, what happens if I change my alpha? All right, so same data, same study. Instead of doing an alpha of 0.05, I'm going to do an alpha of 0.001, right? So it's really, really, really low risk of me making a type 1 error, but it makes it super, super duper hard for me to fail to reject the null hypothesis. So our critical cutoff score, critical boundary is 3.30 and a 0.001, right? And then for 0.05 is 1.96, right? So I definitely reduced my type 1 error because it's really, really unlikely. If I had something in that critical region zone, that's more than likely with such a strong p-value that there was an error. But it also makes it harder for me to have those findings. And given that we had a medium or moderate effect when we did our effect size, I would be concerned perhaps that if I had done a situation of 0.001, I would have made the decision fail to reject. And then I would have done my Cohen's D and saw, well, there should be something. And so then that would lead me back to these ideas of power. All right. So again, hypothesis testing allows us to determine if results are significant or not. And then we use further testing like effect size to tell us the strength of the finding, and also for us to acknowledge possible risks that could have been made by us determining our alpha value, perhaps because of sample size. So if you connect with those slides on power and that video on power, you'll see there's a lot of things researchers have to take into account when doing hypothesis testing.